people don't pick out. This will make a very significant impact on your understanding of the course. So, 6 details that you get from this picture. There are 6 takeaway lessons. Lesson number 1 is that there are distinct layers. The same way that you go through a jawbreaker and it changes color with the layers, the atmosphere has totally separate, different realities at different layers. Some of them are wet and full of oxygen. Some of them are dry and have no oxygen. Some of them have ionizing radiation. Some of them have no gases whatsoever. They're roughly the same density as open space. So the first critical concept is the idea of layers. Now, look at the bottom layer. Students, it's pretty hot in our part of the atmosphere where we live, in the troposphere. Oh, and by the way, you got to know the layers. They are troposphere where we live, stratosphere above, mesosphere above that. The thermosphere sort of melts away into something called ionosphere. And that wasn't in your book, so you'll have to add that word. Ionosphere. Ion-O-sphere. I-O-N-O-sphere. Yeah, so the ionosphere includes the mesosphere and then some. Sorry, the ionosphere includes the thermosphere and then. So, number 2 on our list of 6 observations. The surface of the Earth is pretty toasty. Where does that heat come from? No. Greenhouse effect keeps the heat. Like sweater is not your source of heat. Sweater's not a heat source. If you put a sweater on the ground, it's not hot.
The core.
But a sweater, like a greenhouse, helps you keep your heat.
The core of the Earth.
The core is pretty hot, but that heat doesn't travel very far. Because remember that heat is low quality energy. Heat doesn't go very far. Carlton, please explain to the class.
The sun heats up the ground, and then the ground stays warm because of the sweater.
How does the sun heat up the Earth?
What?
How does the sun heat up the Earth?
How does the sun heat up? Because what happens? I don't know.
Can somebody answer the question, please? Yes?
The rays of UV heat
Come on. We've been over this in this class.
I remember.
You've been over this in like the 7th grade and in like the 9th grade.
Trapping the layers of the atmosphere.
It's not too big.
All right. Are you Snapchatting in my class right now? Little selfie jam? That is me. Look. If this was the heat source, it would be hotter when you get closer. But this is negative 231 degrees right here. You got to get really close to the sun before it feels hot. The sun is no doubt hot. It's really hot, like thousands of hydrogen bombs hot. It's also really far, and heat doesn't travel because it's the lowest quality energy. Light, though, light travels very far. The sun's light is a type of energy. And the Earth's surface absorbs some of that light energy, and you know, it changes form, and when energy changes form, quality goes down, and quality goes down, heat is given off. So, part number 3 that you've got to know. Sorry, part number 2?
Yeah.
There's part number 2 that you've got to know. The source of the Earth's heat is the surface of the Earth itself. Absorbs sunlight, gives off heat. Number 3 is a good one. Gravity works on all atoms. It works on solids. So this marker will be pulled down to the Earth by gravity. It works on... Shut up. I'm just kidding. It works on liquids. So this water will be pulled down to the Earth by gravity. And of course, it also works on gases. So if you could please look up, you'll notice that almost all of the atmosphere is very close to the surface of the Earth because, you know, gravity is grabbing it. Now, gravity cannot grab the most active gases. So here's a wacky thought. Gravity sorts the atmosphere into the laziest gases down here where we live, and the most hyperactive volatile gases at the top where nothing lives. Also number 14, yes. One of the six facts that you take away from this image is that we in the living part of the atmosphere have all the lazy gases. And almost all of the gases are below 13,000 feet. 90% is below 13,000. 99% is below 30,000. Perhaps some of you have heard that there's not a lot of oxygen on the top of mountains. Have you guys heard about that? Altitude sickness, oxygen deprivation. Here's an interesting fact. Please look up. If you look at the diagram, 90% of our gases, including all the oxygen, are below 13,000 meters. Oxygen is right around 20 or 25% when you reach the top of Mount Everest, which is right below 9,000 meters. So if you're on Mount Everest, you're like please look up, right there. That's Mount Everest. And at that point, there's almost no oxygen. Please look up here. We have 100% of our oxygen supply at sea level. We have about 20 or so percent at Mount Everest. Now, a lot of people think it's a straight line. So as you drive toward Mammoth, you start to feel elevation sickness. The fun fact is, that's not elevation sickness you're feeling. Because if you speak calculus or if you speak geometry, you'll understand what I'm saying. The volume of a sphere is a cube root function. It's not linear relative to radius. So you don't lose a lot of oxygen by going up 6,000 or 7,000 feet. You barely lose any. If you're standing at Mammoth Lakes, California, you're at 7,000 and change. The oxygen levels there are about 97% of sea level. You do not have oxygen deprivation when you're in Mammoth. How many of you have experienced headaches or nausea? That's mostly because of your blood pressure not matching the atmospheric pressure anymore. There's a different amount of gravity. There's less air above you. What do you mean? There's less gravity, I guess. You're technically a little bit lighter up there. Everybody thinks they gain weight when they come down to them. What most people think is elevation sickness is either just their blood pressure not being right. You should drink a bunch of water, and if you drink a bunch of water within 24 hours, your body will regulate its salt balance, and you should just try to pee a lot. If you make yourself pee a lot, your kidneys will figure out the right salt balance to get the right blood pressure, and then your headache goes away. So that's not oxygen debt. You don't really experience a significant supply in oxygen until you get to like 12 or 13,000. When you get above 15 or 18, then it starts to get pretty steep. Above 18,000, every footstep you have measurably less oxygen. You lose way more oxygen from 19 to 20,000 than you lose from 0 to 15,000. Yeah?
You said there's like 100% oxygen at sea level and there's like 20%. What do you mean?
100% of your oxygen supply. So it's 28% of, but it's actually, at the Earth's surface, it's probably more like 30% of the atmosphere.
So 30% of all oxygen on Earth is at sea level?
No, 30% of all gases at sea level is oxygen. I think. And you figure out the right number on Google, I'm guessing 30.
100%.
It's not 100% saturation of the atmosphere, it's 100% of our maximum oxygen supply.
What happens to the nitrogen level?
Sorry. Yeah.
At what height of sea level is there not enough oxygen?
Well, for a second you could survive anywhere, right? So it's oxygen level. It's oxygen level versus time. On the top of Mount Everest, if you take a nap, you'll never wake up. Yeah.
You have like go up there and oxygen get the top.
Yeah, I mean, you can make yourself survive it for a while. The first man to climb Mount Everest without supplemental oxygen was Reinhold Messner, and he probably spent more than an hour up there. Actually, no, but it was more than 15 minutes up there. But most people, when they get up there, they touch the summit, they take a couple photos, and then they bail. By the time you get up there, you have to rest every 6 minutes, every 6 steps usually. So most alpinists who are in good shape and have lungs like this and have a heart like that, most alpinists will go like. It's like breath holding. So like you do for diving, you know how you like hold your breath and go down, you gotta come up, you gotta regather your breath. But wait for your breathing to calm down and your heart to chill. That's like 6 steps of walking at elevation, at extreme elevation. So you can imagine how long you can keep doing that, right?
Fascinating.
So one thing you got to know is that each of these layers has different gas blend. The same way that oxygen goes down, almost everything goes down. 90% of the atmosphere is below 13,000 and 99 is below 30,000. Next, the fourth little fact you should know is that ozone is pretty volatile. Ozone is one of the ones, please look up, ozone does escape gravity for a while. You know how this is sorting things based on their volatility? Ozone is pretty volatile.
What does that mean?
It's like actually how much it's dancing. So ozone is pretty energetic. It's kind of higher up in the stratosphere. And a fun fact about ozone is that ozone blocks ultraviolet. Ultraviolet C, the really gnarly one, the one that can fry you and turn you into gases and juice. So look at the temperature. It's hottest at the surface, then temperature drops off as you go up to the stratosphere. And as soon as you enter the stratosphere, you see how the temperature starts to climb again? That's because ultraviolet is colliding with ozone. That also means that ultraviolet is blocked. So down here where we are, there's no ultraviolet C. You guys ever seen sunglasses that say blocks 100% of ultraviolet A or blocks 100% of ultraviolet B? If you ever see glasses that say blocks 100% of ultraviolet C, don't buy them. You don't need that. Unless you're planning to be an astronaut without a helmet, nobody needs ultraviolet C blockage. There's almost no ultraviolet C at the Earth's surface. I've seen it. I've seen it.
Why would they even make
I don't know. It's a gimmick, right? Right. What I mean to say is it's completely right. It's unnecessary. Whether or not it blocks ultraviolet C is irrelevant because there isn't any here, so who cares? You need sunglasses for it. What you do need is ozone. So if you can look up there, that ozone, that's our sunblock. That keeps the ultraviolet C from hitting us. But above the ozone, there is ultraviolet C. So chemistry is totally different above the ozone layer. You see, we had layers like a jawbreaker. We had heat sources of the Earth. We had 90% is below blah, blah, blah. We had ozone layer is in the stratosphere. And now number 5, because the ozone layer is in the stratosphere, above the ozone, there's all types of ultraviolet. Chemistry above the ozone layer is totally different. Gases that survive down here fall apart up there because the ultraviolet is too much energy. It splits all sorts of chaos. It's too gnarly up there. Yeah. And so something funny that happens, there are gases which are stable in our part of the atmosphere, but they're still volatile. So they will rise up, break into parts, and come down as little pieces that are still. Volatile compounds go up and the raw ingredients come down. It's like a food disposal in the sky. Whatever you can get through the ozone, ultraviolet will probably change its chemistry. Yeah?
Is the only stuff that gets through the ozone the elements light enough to create gravity, so like fluid and heavy?
I'm not really clear on the details, but I would imagine that and compounds that are super active. Finally, number 6. Water is contained to the troposphere. So this layer, this is what we call the living atmosphere. It's the living atmosphere because this has the right temperatures. This has no ultraviolet C, no ozone, and all the water. Once you get outside of the troposphere, our part, once you get outside of this one, above that airplane, life doesn't work, chemistry doesn't work, water doesn't happen. Things out here are totally different. You guys know that dude that jumped out of a...
Felix?
Whatever, Baumgartner? 33,000 feet or something? Anybody know the number?
Oh, that's higher than that.
35,000 feet?
Yeah, 35, 33.
He was like right here. And he was already wearing a spacesuit. He wasn't wearing a spacesuit for like looking good. And that wasn't about temperature or oxygen. He was only there for a couple minutes, so you could survive cold temperatures for a couple. A wetsuit would have been enough for temperature. And for oxygen, 2 or 3 minutes, you can just get like a little bottled tank with a little breather, you know, like a little scuba tank. 3 minutes, I could pretty much hold a breath. Take 3 breaths maybe.
Well, for your quality.
So he did not need the astronaut suit for oxygen. He didn't need the astronaut suit for temperature. He needed the astronaut suit because life up there is crazy. Doesn't happen. Ozone, ultraviolet radiation, ionizing radiation, nar. If he didn't have the astronaut suit, he would have probably blistered away and he may have turned to gases to some degree.
What about the pressure?
I'm certain that's a pressurized suit to make the jump.
I mean, like without the suit.
Without the suit, he probably would have had burst blood vessels in his eyes, and he might have burst a blood vessel in his brain and had an aneurysm and died. You can train your body to work at most of those pressures, but he would be at 1% of an atmosphere, so that's pretty low. He would be overpressured by 99-fold.
What do you need to see for, falling and then going, breaking the sound barrier and that kind of thing?
I don't know how the sound barrier acts on the body. I don't know about that. That's interesting. Eardrums for sure. All right. Now that we have made some observations about this diagram, and remember, when you're up at Mammoth, don't complain about the elevation. You're just being a whiner. I need to talk about number 13. First of all, what's the answer to the warm-up? What's the difference between weather and climate? Climate is a long-term average. Weather is a single event. I hate to keep using the same analogy, but I really can't think of a better one. Whether or not LeBron James makes a free throw is an event. So LeBron James comes out to the free throw line, throws the free throw. He might contribute to kick the ball. Whether or not he makes that free throw, that's like weather. It's an event. That doesn't mean his average for life is horrible if he misses it. And that doesn't mean his average for life is perfect if he makes it, because that's just one event. Lifetime average, that's a lot of free throws for a basketball player like LeBron James. Do we agree with that analogy? I get really frustrated when people ask me, oh my God, it's so hot today. Is this climate change? And I always think, I know what people are trying to say. It's not that I don't get it. It's that the words are so misused. It belies an ignorance that is just telling. Imagine you see LeBron James at a basketball game. He misses the free throw. And you ask the person next to you, wow, is that because of his lifetime average free throw percentage? That person next to you would be like, do you have brain damage? Like, those are not the right words for this. Get it, brain damage. Yeah. It's a punk rock record. Look it up. Weather is like little blips, they're little events, they're facts. And climate is the average over a long period of time. And in a period of global cooling, you could have a really hot day, and in a period of global warming, you could have a really cold day. And you don't describe an event by attributing it to an average. All events are part of an average, So if you could say LeBron James is getting worse and worse at free throws, then it's like, oh yeah, well he's probably going to miss some more of them today. So as the planet's getting hotter, on average, more days will be hotter than average. That's just how you describe an average. Remember also that weather is regional, and our planet's atmosphere is complicated. So when we start talking about global warming, somebody's going to be like, oh, but it was really hot in that one city that one day. Well, that's nice, but first of all, that's weather. And second of all, some regions of the planet will have a different change than the average for the planet. It's wacky. When the planet on average gets warmer, Europe on average gets colder. Global warming means European cooling. And I can explain that to you. Yeah, thermal conveyor current, thermal Haley current. We'll look at that in there. Well, people have known about that since like the 50s. All right. So let's talk a little bit about weather. All the weather happens because of changes to this. And I'll be lucky if we can just finish explaining this today. If you change, yes, that's number 13, see? If you change what's happening here, you will change weather. So weather is the tweaks of that system. Anything that happens to change this is what we call a weather event. This is called the picture on the screen. Stop asking. So, yeah, this is called a drawing of the Earth. But they're called convection cells. Those are the 6 convection cells. And look, in order to explain that, I got to do this. And in order to do this, actually no, in order to explain that, I got to do that. And to do that, I got to do this. And to do this, I got to do that. But to do that, we will start with 4 basic principles of physics that I'm sure all of you already know. Number 1, heat and pressure are basically the same idea. When you heat a substance, you make it more active, and so you have more collisions, and so it spreads out, and that's what we mean by high pressure. If you've ever been to a concert, I'm sure you've noticed that people are pretty crowded on the floor, but where you've got a mosh pit, they're hyperactive, so they're using up more space, higher pressure in the mosh pit. More energy, so more collisions. Everybody understand that? Yep. What, that's not true?
No, that's an awesome analogy.
Thank you. If you take the 5 wackos in the mosh pit and you cool them down, they don't occupy very much space, and the concert will squeeze around them. But when those 5 weirdos start bouncing around, they're going to expand their space, creating pressure on the rest of the audience to move away. Everybody knows that. Second of all, if you are not one of those highly active wackos, then you will go away from them. Gases move from high pressure to low pressure. The same reason that a gentle, calm, tired concert goer will move away from the mosh pit is, whoa, 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 too much, whoa, bro, chill it. And so you just kind of move away. It's like, oh, I'm going to go kick back over there where everybody's more relaxed. That's me. That's why I don't even go to shows anymore. Too much noise. Number 3.
Wait, so what is that H?
From high pressure to low pressure. Those are high pressure zones and low pressure zones. Duh. Number 3, hot air rises. Hot air rises is just another way of saying 1 and 2. Because the heat source is the Earth, and everything goes from high pressure to low pressure. Heat is pressure. Gases go from the heat source to the not hot area. So hot air rises. Number 3 is just another way of stating everything we've already talked about, but everybody here should know that hot air rises. And number 4, I've made up a new word, and I'm going to keep using it because I really like it. As hot vapor rises, that means water vapor, vapor. And you should be warned, I'm going to pretty much use that forever. I will not rest until that's recognized by the Oxford English Dictionary. As hot vapor rises, it's further from the heat source, so it cools off. And you know that when water vapor cools, it condenses. If you can remember those 4 rules, then all of this will make sense. And if you can explain one of these, then you can explain that. And then if you can explain that, you can explain that, you can explain that, you can explain that. So here it comes. As air moves across the surface of the earth, it picks up vapor and heat. See? Picks up heat and vapor. Now that it's hotter, please look up. Hot, wet air will rise. As it rises, it will cool. As it cools, it will condense. As it condenses, it will give off its heat. Because you guys know that when you add heat to water, it expands into gas. When you take away the heat, it condenses into liquid. Everybody knows that, right? So the heat is lost to the atmosphere. That's called latent heat release. That's a vocab term. And now that you have cooled and dry air, it will fall and sink. And as it gets closer to the heat source, it'll heat up and expand and move away. So, now look, the places where the air is leaving, like leaving the surface or leaving the atmosphere, those are low pressure. The places where it's slamming into stuff, that's high pressure. So slamming into the earth or slamming into the clouds, that's what pushes the other stuff out of the way. This is driven by heat. The energy source is the heat. This is the energy source of a convection current. They're called convection currents. You guys remember, convection ventilation in your house was when you move the air based on heat and cold, right? So heat, driven by heat. Please notice, if you're an airplane, you'll fly this way for most efficiency. But if you're a car, you want to drive in the opposite direction for most efficiency. Does that make sense to everybody? Because at the surface, it moves this way, and at the top of the atmosphere, it moves that way. Everybody got that? Yes? Yes.
I know wind has a lot to do with heat and distribution and everything, but does it have anything to do with pressure?
When air is moving from high to low, that's what we call wind. This is surface wind, and this is jet stream. You know why the jet stream is faster than the surface wind?
Bigger difference.
Less gases.
It's a bigger circle. So if you're going to cover this one in a little while, you've got to move a lot faster to cover the longer arc. Like that. All right.
How fast is the jet stream?
Actually, the jet stream is also faster for a few other reasons, but it's like 20 to 30. Wait, 200 to 300 miles an hour.
It'd be so fun to just be in it.
Be in an airplane. All right.
No, just to be in like a circle.
Now, students,
Fetal.
do we need to discuss the convection cell anymore? I will review just once. The sun's light reaches the surface of the earth, absorbs, gives off heat. That heat is absorbed by the air above it, so it picks up heat and moisture, so it rises, cools, condenses. Now that it is lazy and run out of energy, it'll be pushed away by this high pressure, so it'll go, it'll just kind of fall away. Where it falls, it packs into the ground, making high pressure, which creates surface wind that's going toward the hot place where everything is rising. You get rainfall where it's hot. It's usually dry where cold air sinks. Everybody got that? On our planet, there are 6 of these. They're like donuts or life preservers going around the Earth. On a different planet, with a different distance to the sun and a different amount of water, there could be 7 or 20 or 3 or 0 or 5 million, I don't know. Our planet has 6. There's no logic to those 6 that you need to know beyond the fact that we're on Earth and Earth has 6, and it's 6 because it's Earth. And that's all I can tell you. But those 6 follow a very simple rule called friction. Imagine that this is a single cog. So it's spinning this way, okay? Here's my spinning cog. What will happen if I bring another one close enough to touch? It'll spin in the opposite way. So the friction. Right? Now over here, where this one's spinning this way, what will happen if I bring another one in contact? So you've got double rising in one place and double falling in another place. If I keep going, this is fun. If I keep going, the next one over will have double rising. Everybody got that? Yeah. And if I keep going, this is so good. I can do this for days. Okay. I can't stop. That was so good. Is that on video, dude? Was that on screen? Nice. All right. Check this out. Most of the Earth's heat is coming off the equator because the equator gets the same amount of sunlight every single day. That's how you know it's the equator, because it's equal day in and day out. 12 hours of sunlight every single day. So the main heat source is the waste belt of the sphere, the equator. You've got rising hot air. You see the equator has the most risingness, hottest air. So the equator has this giant heat engine. And so because you get rising here, the equator makes a whole lot of rain. Everybody got that? Because you get falling dry cold air, the 30s are the dry latitudes. And because the other half of that circle is double rising at 60, you get a lot of rain at 60. So check out this amazing news flash. As a photograph taken from space, 60 degrees north is extremely wet. 30 degrees north is a band of desert across the entire planet. 0 degrees is the wettest. 30 degrees south is another band of desert. And there's not a lot of land at 60 degrees south, but that's the rainiest ocean, for sure. The poles are both deserts. See that? The wet and the dry and the wet and the dry. Looking at a satellite image of the Earth, you can, on average, find the driest and the wettest places because of this. And you can explain those because of this. And you can explain that because of these 4 rules. Anybody want to stop me for anything? Or I can keep going. Yeah.
So does it rain in
Anybody want to stop me for actually saying something or asking something? Yes.
When I stayed in Chincha Alta, there's like a town not that far where apparently it's never rained on record.
That sounds surprising, but fine. Yeah, I mean, there are extremely dry places. Is that on the Altiplano? Border of Chile?
Yeah.
So I'm going to guess that that's probably 30. Do I have time to check? No, I don't have time to check, but we can find out later. It is? Good. Okay, now. How much time do I have? 1 minute? 2 minutes?
1 minute. 2 minutes.
Only 2 minutes?
Now 45.
Let's do a dance. Do this again.
Time is but an illusion.
Attention Miss Boston class, period 4 and 6. Please go to the computer lab, room 34. Again, Miss Boston class, period 4 and 6. Please go to the computer lab in the third
I'm
floor.
sorry, students, that I won't be able to explain why I'm not impressed by Columbus. When we come back tomorrow, will you please ask me to explain why I'm not impressed by Columbus?